So everyone, thanks for joining today. It's really my pleasure to welcome Abhishek Dubey from Vanderbilt to Florida Atlantic today. Abhishek is an associate professor in the Department of Computer Engineering, Electrical Engineering, and Computer Science. He's also a Chancellor's Faculty Fellow at Vandy. Also a senior research scientist with the Institute for Software Integrated Systems, ISIS, at Vanderbilt. In his spare time, he runs Mobius AI, which is a startup company at the intersection of transit and artificial intelligence. He's recently just completed his rotation at the National Science Foundation, served as a program director, played leadership roles in CPS, in smart and connected communities, and also in the civic program, all of which I think have been re-architected.
Basically, sister programs.
Okay, all re-architected largely under Abhishek's leadership. So it's a pleasure to have you here today. You're going to be talking today about neurosymbolic AI and smart cities. We can't wait. Welcome.
Thank you very much. And it's really, I'm very glad to be here. And thank you for inviting me. Thank you, Nicole, for helping. And it's really good to meet all of you. I knew of your work as a program director because I had the internal way to actually look at a lot of the work that you guys do. I also actually met Jason when he was at NSF. So I really think that you guys do really good work and it's awesome. And it's an opportunity to come and talk to you. And hopefully this actually leads to some more collaborative work in the future. So I try to make my slides a little bit at a high level, but sometimes a little bit on the lower level. Depending on how you are reacting, we can skip and change things. And feel free to stop me if you have questions, okay? And Nicole, if we are actually running out of time, please tell us that, now stop talking, right? So, okay, one of the things is, what's the picture on the right? Okay, this is really from a long time back, my work through NSF and cyber physical systems. The idea is of feedback loops. So we think of cities as feedback loops, infrastructure as feedback loops. So what that means is you sense, you decide, you actuate, and then you sense again, and then you decide and you actuate again. Now, typically feedback loops, people think of them as milliseconds, seconds, minutes. It doesn't have to be. It could be 6 months. It could be 1 year. And that's where you actually go into more from operations to planning, right? And I actually met a few of you folks earlier today, and they do urban planning. Urban planning can also be articulated as a feedback loop if you do adaptations over time. So this is the classical example. We think of cyber physical systems and we think of cities as this thing that there is sensing, there is computer networks, there is computations, and there is humans. So sometimes people also call them human cyber physical systems. But actually, to be honest, a lot of cyber physical systems are human cyber physical systems. Right? If you consider, because these cyber physical systems are being built for humans. Humans are right in the middle of it, and they have to be part of it, right? So now the big question that we ask is that as we are building these systems and these systems are interacting with each other, what does optimality means? How can you make them efficient? How can you actually run them efficiently, right? So these are some of the questions we ask, right? To just give you an example of some classes of the systems that I deal with and the problems that come in and what are some of the optimality questions. Let's take a look at the few things, right? So specifically, if you consider this, right, this is a very, very old newspaper article, right, from 1930s. The idea is that when the motor cars were really started coming in and everybody realized that they are hitting people, right? People are dying about it. So one of the questions is, how do you respond to an accident? Now, why are we talking about it? One of the biggest challenges is, as I will show you, the number of accidents that happen over time are a lot, but accidents themselves are sparse, means they happen only so often. Now, you have a limited number of locations, limited number of resources. How do you respond to them? What do you do? Right? This is where optimality actually comes in. If you see this picture on the right, this is not a picture of roadways of Tennessee. This is a picture of all the accidents between 2017 to 2023 in Tennessee. There is no single roadway where an accident didn't happen. This picture, we didn't model the roadways, actually just modeled the accidents, and the map of Tennessee appeared. This is my thing that I was working with Tennessee Department of Transportation. This is to show you the volume of accidents, right? But the problem is when you actually start taking a look at it and plot a snapshot, a time window, let's say just a month, right? And you plot some of the roadway segments. These segments are basically mile segments of highways. Then when you look at this picture, what you see is like a starry night, right? It is not just white all over the place. White is where an accident happened. Now, here's the first question. If the traffic accidents are so rare, if we are going to optimize something, we must be able to predict something. How do we predict this? So this is actually something why I ask in my, I teach intro to AI, sometimes and other times in CPS. I ask students, what is a good measure of prediction in this case? Sometimes students say accuracy. It's a very bad measure because in this case, if I just tell my AI or my model to just predict no accident ever, that's it. It is 99% accurate because that is what is happening in this black picture. And actually you can't work with that. So you need something else. So we need something that you all probably know, F1 score, to really try to understand the precision and record, right? And when we start looking at this, this is just an example of these classes of cyber physical systems. A lot of time, the data that we are working with is very, very sparse. A lot of time, the communications that we deal with, the networks are very uncertain because networks themselves can actually fail. And the whole thing, the whole environment is just constantly shifting underneath us, right? It's constantly changing. So when we're talking about optimization, that's the system we are dealing with. And you have to consider this with the classical way till at least below 2000s, the problems have been dealt with. They've been dealt with static optimization, what sometimes we also call operations research. So it's a pretty good way of dealing with it, but it deals with static snapshots. The problem is there, let's figure out the best way to handle it. Now, if the problem changed, you have to reappear for the exam again. And problem is changing continuously underneath us. It's not that every 6 months, it's changing every 30 seconds. So how do you adapt? How do you plan? That actually becomes a big problem. If we go away from emergency response, a lot of my work is in public transportation, as Jason mentioned. So here's a picture of, on the extreme right is a service that is called paratransit. Paratransit is a service in transportation sector that is responsible for moving people who have disabilities, who have certain medical issues, who cannot use the regular transit. By law, they have to be provided paratransit services to go to their appointments or go to their medical. The reason the law says you have to do this is because every able-bodied person is actually able to take the public transit. So they are getting the benefit of these taxpayer services, right? But if you are disabled, you can't. So then the rule says, if you are within 3/4 miles away from the stop where there is, and you live there, you can call them up and you will be able to actually use the service. Now, the problem is if everybody starts using the service, it becomes highly inefficient. How do you actually operate this? So what's the way to run this? And then the rule says that you must provide the service that the wait time is under a certain limit. So now the traffic can change, weather can change. You have to provide that. On the right-hand side, on the top left is the typical fixed line bus from Chattanooga, a city that I work a lot in. Now, these fixed line buses, you typically try to run them at a frequency, at a particular schedule. But you plan something and the reality on the day is slightly something different because the traffic changes, the light pattern changes, the red lights, it stops the bus. So what you thought would be 30-minute gap between them sometimes becomes 40 minutes, sometimes become 15 minutes. So what you thought is the ideal way to bring people and move people is not what is happening on the ground. So now you must adjust and hold the buses. So again, it becomes a dynamic problem, right? On the bottom right is, so electric buses, hybrid buses. These are pretty cool. We are bringing them on board. A lot of cities are actually doing this. But now becomes the problem, how do you charge them? Charging these buses, this is a bus in Chattanooga. A lot of these buses have plug-in batteries inside, and it will take around 3 hours just to charge. So now you have to decide when to charge because it takes time. So they are not available to the route. If you actually charge all these buses at the same time, you load up the grid. So you can't. So you see, a lot of the time, these classes of problems are coming where there is something that you are trying to optimize. There are certain constraints. Looks like classical OR, but you have to do this adaptively again and again and again and anticipate what is changing. Right? So this is just an example in transportation, disruptions, accidents, everything actually changes, right? You have to do the headway control. When you are doing initial planning, you have to figure out where the chargers should go, which buses should be allocated to which route. All of these are effectively optimization problems, right? Finally, if we are just talking about the infrastructure, one of the biggest infrastructure, sort of the miracle of modern engineering is power grid. We don't think twice about it, the electricity, the electrons that are here. But actually, you should think about it. How in the world is this coming here? It is a very, very complicated system. And I was telling some of you, like I personally in Nashville, we had just had an ice storm, complete shutdown. There were power failures completely. I was out four days completely without power, and it was cold. It was 20 Fahrenheit outside. Inside house, it was cold, right? So then you like, oh, now I know how important electricity is, right? And by the way, I'm selfish. I'm an electrical engineer, so obviously for me it's important, right? But then when you start looking at this infrastructure, why are we talking about this? Generally, this infrastructure was already bad, the power grid infrastructure. These are just some ratings from the Association of Engineers, right? Our power infrastructure ratings are not very good. And then we are throwing EVs at it. We are throwing data centers at it. So what can you do? Again, it is about optimization. So the reason is all of these problems leads to this thing that the modern cyber physical systems that we are talking about, we want to talk about the actuation as an optimization loop. And this optimization has to happen continuously over time, again and again, as you sense the environment, as you sense the state variables, right? So you really need this adaptive optimization. Now, obviously, one of the easiest way you can actually say this is, I'm going to apply learning-based approaches. Learning-based approaches, classical AI, machine learning, reinforcement learning, you can apply. Most of these approaches are neural-based approaches. What that means is that you want to train a neural network where you give the input states and the outputs are the actions that you should take. And ideally, when you do it again and again and again, it is optimal. Right? This is the classical thing about reinforcement learning. Okay. And it works pretty well. But generally, in these classes of systems, what you will find is two things. One, you will actually find that there is really inherently no notion of constraints in these systems. A lot of times when you look at it with pure RL, you may even do physics guided RL again and again, but there is no guarantee that it will not violate constraint. And I asked it this way to the students who are really, really happy about RL and come and say, would you bet $1 million that it will not make a mistake? And I will take your $1 million if it makes a mistake in 100 tries, and they will not take me on it, right? So that is the problem that we are dealing with. Then classically, on the other side of things that had worked very, very well, these are the classic operations research methods, rule-based methods, mixing integer linear programs. You can put solvers, you can actually get answers. Now the problem becomes, every time I set the solution up, it takes time. I get the answer, and then the state changes again. How do I do this again and again and again rapidly? So it becomes a problem, right? So the reason for this is to really say and sort of motivate what does neurosymbolic means actually. Neurosymbolic means you're trying to bring these two things together. And neurosymbolic is where the modern CPS science of planning is actually going. right? You're trying to learn these two systems and make sure that the constraints are being validated. Constraints are right there in the check, but there is something else that is happening, right? So when you put this, you can actually plan ahead with the uncertainty. And I will show you some of these things. A very classic example of a neurosymbolic approach is something like AlphaGo. AlphaGo was the program that was not designed to be neurosymbolic. They never thought that it is neurosymbolic. So AlphaGo was a program that was created by DeepMind around 2016, 2017 that beat the world Go champion, right? There's a pretty nice Netflix documentary on it. What did it actually do? And then from AlphaGo came AlphaZero. So AlphaZero is where the generalization really happened. It could play any board game. So what did it do? At the basis of it is there was a neural network that says, I will give you a state. State is a game board, and it will give you the value of that state. So what does the value means? From this position of the board, how many times you won? That's it, right? And how did you do that? You just played again and again, or you had lots of old data, and you can figure out the value, right? Once you have figured out the value, what is next? Then you actually bring in something called Monte Carlo tree search. Monte Carlo tree search is actually nothing new. It is a very old concept that we used to call model predictive control. Model predictive control is take a state and take all the possible actions, take the next state, take all the possible actions, take the next. You see, you will fan out widely, right? When you reach the leaf nodes, figure out what the value of these nodes are by either the game finishes, whatever happens, and then you back propagate somehow you have to attribute to the initial state what was the value of the action that you took that led you to most of the winning. So if an action you took on the left led you majority to the winning state, that action is more valuable versus an action that take you majority to the loss. Now, in most cases, when we do model predictive control, this kind of system becomes really widely difficult to explore because it explores everything. What Monte Carlo tree search did is, hey, I will bias this search towards things that are better in winning. This is an approach called multi-armed bandit in game theory, and it started biasing towards things that are giving you a better exploitation. So this is what you may have heard about exploration versus exploitation, and it doesn't do every branch. Okay. Now, another thing it did in Monte Carlo tree search with AlphaZero was rather than leaving to the end of the play always to finish the game, they asked this neural network they had learned somewhere in the middle itself, hey, what is the value of this? So you save time to explore to the complete depth. So now you mix the Monte Carlo tree search with this value network, and suddenly you actually have an AI that can actually figure out the importance of an action. So, okay, backtrack from there. AlphaZero did this on discrete actions. Now, our challenge is we have to do this on continuous actions because cyber physical systems, the action space is continuous. It's not discrete actions, right? And the other thing is where will that value comes from? And here's the most important thing, where the symbolic part comes in, these actions have to be feasible. If an action is infeasible, a constraint is violated, you prune that branch immediately. So now all the action sequences that we take are feasible. The value is coming from the neural side, and then we can actually mix. So this is the basic strategy that we figured out that it works, and we could do again and again and again in all the problems that I showed you. So if I can distill down from everything that we have done, the basic thing is trying to figure out how to use AlphaZero in real world. That's it. That's the summary of my work, right? So when we do this, you start figuring out that there are lots and lots of differentiating architectures that you have to use because sometimes because of this continuous thing, it just doesn't scale, right? So sometimes you have to do hierarchical planning. So you take a large problem and break it into zonal problems. In transportation, this works very, very well because we can actually do zone-based transportation planning, right? In a city could actually be divided into sub-regions, for example, right? Sometimes none of this works. Then we have to do decentralized planning. Decentralized planning means give each agent, let's say, fire station, its own agency to plan what it has to do. each bus, each microtransit is on its own agency. But now there has to be some coordination between them. So this is where it becomes really, really nice problem. How do you do a decentralized planning and provide the guaranteed answers, but it is scalable. So these are the general methods that we actually use. But as we do these methods, some initial problems starts coming in. As I said, high dimensions. Sometimes we have to do long horizon planning. So while this alpha zero and stuff, we can actually stop at small depth of the tree. Sometimes we have to go, for example, when we do power grid planning, we have to go to the end of the month. And our planning horizon is, let's say, every 15 minutes. So 15 minutes to a day, and then a day to a whole month. That depth just becomes too long. How do you tackle that, right? How do you integrate the constraints? So biggest thing when we are dealing with something like cyber physical systems, you also have to deal with partial observability. Partial observability actually means that you don't really see the state variables directly. So you don't know how to calculate the reward yet. Because I don't know my state, you have certain observation, and you have to also solve the state estimation problem. Now, state estimation problem, for those of you with a slight control background, you will remember particle filters. You have to throw particle filters at it. As soon as you throw particle filters at it, if thing was not already blowing up, thing blows up, right? So then figure out like how do you actually solve this? But this is a nice thing in this world, that if you are looking at problems to solve and writing papers, these problems are that hard because most papers that you will find are making some simplifying assumptions. So often people say this, right? Hey, there are 100 papers already in this area. Before I started working in microtransit and from 2015 onwards, I heard this, lot of papers in DR, demand responsive transit. And I said, I don't care, because I can always go and basically challenge their assumptions and then change their assumptions and say, I will go a next step, because you haven't solved the full problem yet, because nobody can solve the full problem. If NP hard is hard, I don't know what this is. This is hard to hard to hard. So there's always some slack. You can move a little progress. And then if you can show the impact in real world, suddenly you have papers, and our papers started publishing, right? So this is the nice trick in this work. You are never saturated. You can always do something else, right? And then when we actually do with this, you get finally these kind of problems in Austria. This is actually from Carla, one of my students trained this. And what is happening here is, this is just a simple autonomous system, just to show what we have to deal with when we do these plannings. He trained a simple agent that can actually figure out how to drive around a city track to find speed. Then what he did was he changed the frictional constant on the road. Now suddenly this well-designed policy is no good anymore. Because imagine this, if it's slippery and you go with such a fast turn, what will happen? You go outside. So now here's the question. This is also partial observability. You don't know that the friction changed. How do you gain? How do you learn? Learn safely and still adapt your policy. You do not have time to retrain. You don't have time to redesign the system. And this is just a toy example, but now come back to my city. I designed the city fire response. I worked with Nashville. We did the microtransit, and suddenly 4 new condos opened up. Now suddenly the demand changed, right? The traffic patterns changed. How do I recover from it? We cannot just go back to the drawing cycle every 3 months. So we need to actually solve these problems.
Which energy are you using to solve these problems at the minute level? You know what I'm saying? Is
Yeah.
it overall, is the energy that is being expended into solving these minor, I don't want to say minor, but micro impacts?
Yeah.
Is it worth it?
I think so, because I'll show you the impact. So we have been able to work with the city and show them that the results are much, much better than where they were. So at the end of the day, you can convert that into the dollars for the city. Like, okay, how much dollars saved? And then they don't care about all of this. This is mumbo jumbo. They don't care, but they have a system that is actually saving them money and still providing better service than what they were providing before. Now they are happy. So I think that's where it's impactful, because at the end of the day, it is serving the residents of the city and actually helping them. right? So that's why, and to the students, it is worth it. It actually gives them really good publications, right? So for an example, these are just 3 publications from last year that we had. The first publication is adaptive MCTS. So we actually showed in such non-stationary settings, how can you do a risk-averse learning, risk-averse exploration, and then retrain the MCTS very, very quickly. So the way in the background was, we were learning a Bayesian neural network that was acting as a surrogate for a transition system. So very, very quickly, it can learn. The second paper was basically, how do you actually do particle filter belief updates under non-stationarity? So particle filters belief is basically what is telling you the belief distribution of where your state is. And typically you have to resample as new observation comes in. So we showed how do you do it much, much more efficiently. So what we did was, we actually combined hybrid system reachability analysis with this. So we combined a lot of particles together into convex sets. So we never moved particles, we actually moved convex sets now forward. So it suddenly became very, very efficient. And we can actually do state estimation. In the Carla and F110 thing that I was showing you, it's actually pretty useful because you don't really know the true steer, you don't know the true braking conditions, nothing. So all of those are effectively partially observable problem. Sorry.
And how do you integrate human response to all of this equation? Because that could be different, right?
Yeah. So that's actually, I'll show you in a very quickly in a place. A lot of time it will go into mechanism design side things, right? Other side, it actually goes to the interface side and build enough slack in the system that humans can choose from. But at the end of the day, I will tell you, that is my blind side a little bit, because I am not a trained social scientist. So I don't necessarily do that very, very well. Sometimes I work with the social scientists and I try to understand what they're saying. And then however much I can translate, I translate it into my systems, right? But there is a blind side, there is a gap. That's actually a traditional gap in all cyber physical systems and smart and connected community projects. We used to evaluate them, we used to see them, and it's typically a big problem. It's very, very difficult problem. And the last paper is actually the learned abstraction paper. So we showed how do you deal with large continuous action spaces. And what we trained was basically a VQVAE, which is vector quantized variational autoencoder, to be able to figure out the input to output relationship. So compress action sequences. So 3 actions into macro actions. So effectively the planning problem, we compressed it down and we showed we still do better than anybody else. All of this was actually my teams of students who are responsible for developing the core algorithm. Then I have another team of students who will take the core algorithms to actually the city level impact, because then you start seeing outside what's happening. Right. So let's talk about real world impact. I am not going to go through all of it because, of course, we don't have time. But if you have any questions, you can ask me. So, for example, the incident response that I talked to you about, it is a little bit old work. Very, very quickly, I'll skip that. But the big thing that I'm really interested to talk about is vehicle top rating. We actually showed how to basically make the grid more stable by reducing the peak demand of each building, right? By using electric vehicles, not just as a charging device, but actually as a discharging device. So to a large building like this, suppose you have 100 EVs outside, and all of you, let's say, you drove EVs, you connected, you came in the morning, the building will promise you that by the evening when you go, your cars will be charged. But what it is doing in the day is basically discharging, charging, discharging, charging. And sometimes it is discharging your car because it anticipates you will go later and can charge later. But it is discharging right now because right now the peak demand is pretty high. The electricity is very expensive outside. Now, in a state like Tennessee, it becomes very difficult because we don't have demand-based pricing. It's just pure static. So it doesn't work. But in California, it works very well, right? And we worked on this with some of our industrial partners like Nissan and Siemens to actually do this. Now, in this case, it's really EV actually becomes battery asset. And you can actually start giving even peak backup power. So this is, for example, when my home was out of power, I could have actually discharged into my home, and at least for some time. And let's say a regular Tesla, typical Tesla is 75 kilowatt hours, the old Teslas, right? And a home in a day typically uses 10 units of power. So actually, if you really think about it, if you discharge completely, you can run a home for 6 days, 5 days.
Did you do it?
I don't have an electric car. I'm asking for more salary to buy electric car, but hopefully, right? But these things are possible. We are trying to do this with Nissan in California, and it is actually working very well. So our story basically is just like this: like you bring your cars, you connect to the buildings, and building basically draws power from the grid, and your cars are the reservoirs effectively. Now, quite interesting things happen for the human aspect of things here. That when you look at from the human angle, everybody has this fear that my battery health is being degraded. So we actually showed them that is actually not the case. You can work with the minimum and maximum bounds. You set that up, and till you are working with the minimum and maximum bounds, it actually doesn't impact too much if you're charging and discharging slowly within certain rates. And then you also give some money back to the employees that, okay, not only are you getting free electricity, that's number one. Number two, you're getting some additional money on top of it. And the building still saves money. That's what we were able to actually show to them, right? So Nissan basically start building this thing up, and they have around 5 bidirectional chargers and 10 unidirectional chargers in their innovation office, and all the employees can connect and plug to it, and they can actually charge and discharge. So this has been almost like 4 years of partnership with them to build this thing, right? Now, all of these problems that I've been talking about are here in this charging problem. Same thing. So we are basically building the very similar architecture that we have talked about. Now, this is where it becomes really interesting that a problem like this, you can actually start. It took around 3 years before this to get to this place, but then the publications came one after the other, right? So we were initially able to publish just our simulator. Now, why this simulator? Because simulator allows us to generate these value functions to be able to understand what is happening. Now, simulator was calibrated with the real world, right? But once that is done, we can actually start talking about a reinforcement learning approach. Actually, this paper came first. Then this paper came, the decentralized MCTS paper at ICCPS. Then we actually did persistence. So basically, initially we were solving for 1 day at a time. Then we can solve for 30 days. And the understanding is if an employee is coming to charge, that same employee is returning. So if I charge you a little bit more today, I will charge you a little bit less tomorrow. So you can think. And finally, to your question, this was where the user negotiation actually was stacked on the top of it. So that we showed that actually, if you do the user negotiation properly, and we ran experiments, that it saves more power. Because what was happening was, here you're dealing with uncertainty completely. You estimate from the past data that a user will stay till 5 p.m. But it's Jason. Jason just leaves at 2 p.m. But Jason is a director. If you discharge his car and he doesn't have power, it's a bad thing, right? So I don't want to be the student who designed the algorithm.
I can leave at 2, you can discharge my car.
No, I'm not implying that you are leaving at 2, but that's the kind of example. It becomes really difficult. So then you become very conservative in the sense that you are not going to use the full battery power. You're going to discharge less. But if you get into a contract after negotiation, then you can actually really feel very comfortable that there is a lot of time.
The perspective of this paper is short-term plan.
Yes. So
for this.
So it's for a month. We're planning for a month, but actually a month becomes long. In the consent paper, then we are basically taking at the daily impact and the projected impact of the car across the whole month, and then trying to give some money back to the user to give them that, hey, if you stay till 5 p.m., I'll give you more money. But then if you leave early, you will be given a penalty. right? So do you accept that or not? Right? So obviously we can actually give this to you. So Optimus is effectively an environment where you can play with this kind of V2G examples. It is seeded with real data, right? And it's the whole system. It has generative models, so it can generate more scenarios for you. And then you can actually build your policy engine. So this is where now students can actually start working with the system to just learn and can start experimenting. And then it has a dashboard plus API. The reinforcement learning, one of the big things that we did was we actually initially solved the full answer with MILP. So what basically we have is a generative model that generates lots and lots of trajectories for every sequence of cars for every day across 30 days for the whole month. And you can imagine these 3,000, what we call them chains. These are possible futures. Anytime you are in the month, from that point onwards, you can imagine the chains goes, and these are futures. And you are planning across all the futures and trying to actually take an action that is the best action at this time to be able to give you the best outcome towards the end, right? And that's what we have to solve. But what we do is to actually compute the actual value of this state. We solve an OR problem across all of the possible things. But this is done at the training time. We do not do this at the real time because we can't, right? The other thing was, even in the RL, we actually included action masking. So one of the last layers of RL was this differentiable layers that will actually make sure any infeasible action will be cut out. So it already starts doing neurosymbolic activity, right? And then in the later part, we actually started combining this with some of the others, the MCTS and things. So this was presented in AMAS, right? And we already showed it with just this first verse. So we started around 4% of cost savings to the building, right? But this was not good enough because we trained this for 15 chargers and one charger went bad. Suddenly the whole thing kaput. This was our non-stationarity example, the friction chain. So we spent 1 year on this, one charger failed. Now we're like, okay, scratched our heads. We were expecting this, but it came down, right? So then we actually went to the MCTS. We said, okay, this does not work. So now we need to actually explore. We need to start playing the game in real time. So we took the Optimus, we converted into a neural network state transition system, and we started doing this in real time. But then we had to decentralize it, right? And it actually started working really, really well, right? And it was around 3% cheaper than RL, right? So it did better than RL in the months that RL was not trained for. In this exact settings where RL was trained for, RL was better. But the point was this was more robust than RL. You can actually feel confident that you can implement this in the real world. And even if things change, it can actually handle it. Now, it assumed that somebody is telling it that one of the chargers has failed. Okay? And so that it can reconfigure the simulator, because it uses the simulator as the board to play the action sequence. Then the consent, which is the human negotiation part, the biggest thing was we actually including stochastic MPC and game theory design, mechanism design right there. So a user gets different options, recommended choices, and user can set what their charge levels are, what is the time that they want to leave, and the system will tell you what will be the reward that you can get. And the way it does is it takes that user and it plays around across all the possible future users. And we figure out what is the value of this particular user to me, this particular car, right? And then we take various scenarios, and then we can take, let's say, 75 percentile case, and then we give that back to the user. And that is, we showed actually in the proof that this is strategy proof. It cannot be gamed from the point where it is, right? And then we actually implemented this back. So now every time a user comes, this is the first thing that runs. But once a user has set and chosen, then we actually run the MCTS after that, the same old MCTS. And it actually works very, very well.
How do you assume the data for each user? For example, you said for particular user, you need to plan for this user. How do you assume this?
No, so we, for example, a user one it came, it is plugging in. So we actually ask the user and we have the history of that user, right? So that is for that user. All the other future users are basically in expectation. So we have lots of chains, which are possibilities of what will happen. And then we figured out, okay, we want to figure out the answer that is 75 percentile across everything. So the value of the user across majority of the 75 percentile of the cases, what it is.
So for the history of each user, how much the data?
So history of the each user is basically the data on when do they typically leave. So its importance is not so much on predicting when they will leave, but it is about what they will typically accept, right? So if we do not really know, we just send something. And then the user can tweak the answer and then we learn from there. But the most important part is future trajectories of what the other users have done. Because the value of your car at this particular time has to be evaluated compared to everybody else, what it is happening. And that's what we have.
How many users did you have?
For this particular work, we actually started with around 10 users, right? We studied them, we built this up, but now we are actually working on adding more and more users because we had to go through IRB and everything. This was slightly more complicated. It's not because of technical part. For every non-technical reasons, it was more complicated.
So is this generalizable for other kind of conditions? Let's say we have a different event and they have to have different plans. You said, for example, until 2 p.m. they have to leave. So we have different weather conditions. We have some events happening over there. So did you consider that all these things?
If it is an unknown event, it will fail. No. We only consider the universe that we know, right? What the data has. So we could not plan for unknown situations. So this is only going to work when nothing is unknown.
So it is not adaptable for this condition.
No, so it will be difficult for that. But then you can extend it to try to predict that do you have the likelihood of these unknown situations? Do you have the future chains of the future samples for this? Then you can extend it. But we haven't done that. Sorry.
No, no worries. What's special about this solution compared to the other solutions that are out there that
In the vehicle to grid, for example.
Yeah.
A lot of the vehicle to grid examples that are actually out there are OR based before they actually came. What that means is they will take the current situation and expected situation of the peak demand on that particular day, and they will figure out a schedule. Okay. Now imagine this. They are not actually figuring out that in the future more cars can come. So you can do something else right now because future more cars can come. Now in the OR methods, they were looking at, okay, I know exactly how many cars will come, but you never know exactly. You need to plan an expectation. So that was first difference. The second difference was it is not just about one day. You have to really think about 30 days because the peak demand charge comes across 30 days, for example, right? And doing that in expectation was not there before we came. Before our work came. And that was the primary difference between what we did and what others did.
thanks.
No, that's a good question. So obviously where we want to take this is clearly, we really want to get rid of our simulators and our neural estimator. We want to get it to particular much longer horizon. So we are working with Japanese colleagues from Nissan. Their peak demand sometimes is in some regions is calculated for 1 year. Our systems will die very bad death because computationally it is not possible. 30 days is basically we crawl to an answer. 365 days we cannot. I don't know. So we have to figure out better approximators for that. Also, then we really want to actually make sure that we want to get a formal guarantee. One of the questions we have been asking, which is this, if we can really predict well what is going to happen after the first day, do we really have to plan the 30 days? Can we just go ahead and plan for 1 day and be done with it? And then just assume what is going to happen on the second day and plan? Because if you know, for example, there is a day 3 where the demand is already going to be high.
Yeah.
What's the point doing anything in day 1? Just do whatever you want to do. and day 3 is already going too high. So the way demand charge works is it's like a stuck-on valve. If you cross a particular threshold in a 15-minute interval across the whole month, you pay a penalty. So if I knew on day 7th I'm going to pay penalty anyway, I don't need to do too much right now. But how do you do that really well? We don't right now. So that's why we plan from the beginning to the end. But can you actually get away from it? Right? These are some of the things we want to do, right? And then you can start working on a lot of things. You can actually do complete aggregation, demand and response, multiple buildings. You can actually do foundation models for V2X forecasting and try to bring all of this together, right? I'm going to actually skip out on some of these for the lack of time, but just very, very quickly go. One of the things that we actually do in fixed lines is to be able to set the schedule of the vehicles based upon the traffic time so that the net energy cost is reduced. So we help them charge and we help them decide which vehicle to use where. And we work with Chattanooga and we actually save them $145,000 in 1 year. Basically by just telling them which bus to use on what route and do it strategically, not ad hoc. And this is actually, as Jason said, this was the patent that actually launched my company. Then we do headway. In the headway, the idea is basically how do you manage the gaps between the two vehicles, right? And when we actually started doing this, we started generating guarantees, we started generating systems, and this is right now working. We are working to deliver this with Vigo in Nashville. It's part of a smart grant project from USDOT to actually implement in Vigo. So the way it works is to the driver, it actually shows that you are bunched right now. Bunched means your buses are coming together. You have to hold at a particular stop, or you don't hold, right? There's too much gap. So you need to skip right now this stop, go to the next stop. So we can tell those drivers, right? I'm going to skip the on-demand transit. This is basically the software that we have. We showed that we can actually serve a lot more people, right? With the VMT to PMT ratio is vehicle miles traveled per passenger miles traveled. This is an efficiency. Lower is better. And we can do 25 to 30% lower, right? In the micro transit, in operationally. This is our full software. This is also part of the company now. We actually this is a picture of my student who's now my CTO of the company. He's actually CEO of last week. And he deployed this in Chattanooga. So we take pride in the ability of our students and engineers to actually go do in the city. So we don't just write papers, we go and implement it for them. This is the fire response. We actually implemented with TDOT. TDOT, our Tennessee Department of Transportation, has help trucks. We actually showed them how to station their help trucks and which help truck to dispatch on an accident. And we ran an experiment, it reduced the response time. The way it again worked was we predicted where the accidents are going to happen, did the Monte Carlo research, same old story, just applied on a new problem, right? And finally, this is something that I will leave you with. We go back to the foundation challenge that we have. One of the things that we are figuring out is this non-stationarity is a very big problem. Control theorists have actually known that for a long time, but these AI-based planning tools are not figuring this out. So we said, we don't really even have simple benchmark because I was discovering this across all the different problems. We were discovering this in fire problem, the transit problem, the vehicle. I mean, like, if you came up with a solution and say, here's a better, how do we compare? We go to OpenAI Gym. OpenAI Gym didn't really have a very structured way to introduce changes or anything. How do we compare actually anything? So we created something called NS Gym, which is above OpenAI Gym, and it can actually make different kind of changes that are measurable. You can actually declare whether observable or unobservable. And there is actually a competition running right now in AMAS 2026, which is going to, it was supposed to happen in May and in Cyprus. I don't know whether it will happen or not. It might be pushed out later because of all the funky things that are happening in the world right now. Maybe they will do it in October. But this is a challenge where across the world, people are coming in and they're saying, okay, let's evaluate your inverted pendulum policy with my inverted pendulum policy, your lunar lander policy with my lunar lander policy. And we do things. We say, okay, you design on gravity of Earth, now operate on gravity of Mars. Show me. Your mass, the inverted pendulum, if you guys don't know, is basically a simple mass, and there's a pole on it. And you have to move the mass, otherwise the pole falls, right? And you have to figure out at what speed should you move the mass. Now, what if the mass of the stick is changing because it's degrading? Or what if there is friction changing on the surface? Or what if the gravity changes? So you design your policy on Earth, now do it on Mars. You will see RL policy will fail miserably on this. Typical RL policy. So can people then say, oh, we can do meta RL? We're like, okay, come on, show us. You can. Don't just say you can. Do it in the competition. So it's the whole thing is open and you can do it. Where we are going with this is, we are going to actually introduce transportation applications next in it with our data that it is, and we will open the gym. So it will be the transportation gym version of this and say, towards the transportation policies that you have. And it does not have to be AI policy. It looks like a function, input, output. You can implement your OR policy. You can implement your control policy. But let's compare the output to output, right? And then if it is indeed better, then we can create like a benchmark where everybody can actually compare. So hopefully, if you are joining us at CPSV, which will around May 15th, and ICCPS, which is the main conference, then there will be a tutorial on this gym, how to use it. So with that, I just want to thank my students, my partners. I work a lot with Cornell, with Penn State. I have partnership with them. And then if you have any questions with me, just ask. Thank you.
Awesome. Abhishek. We probably have time for maybe 2 short questions if there are any. I do have one. So I think I'm asking the same question that Madi asked earlier. So in the charging example,
yeah,
you're setting financial incentives for folks to stay longer. I think it's a super cool problem setup. In your model, what does that financial decision-making component look like for the simulated user?
So on that user, one of the things is we have to actually plan for the likelihood of that user leaving. So when that user have actually negotiated, we do not consider the likelihood of that. So we don't become conservative in all the chains that user leaves at the time that they contracted. That's the first thing, right? The second thing is, how did you come up with the value that you give to the user, right? So we actually simulate various different situations every 30 minutes from the time that the user arrives to the time that they can leave, and cross multiply it with all the future chains that we have. So suppose there are 50 scenarios that you have, 50 into 300. So that's all the situations, right? In all the situations, then we converge and we say, okay, in this interval, if you leave, the value of your car's battery is this much. So we calculate it with you and without you, right? And then you can actually compute the average of that and then start telling you that, okay, I believe if you can stay up to this point, that's your value. If you stay up to this point, that is your value. And then portion of your value can be returned back to you.
Right. So that's the piece that I think is super interesting. So I'm curious if your model includes the impact of that potential financial return on the agent's behavior. So because if you
no. So we actually just assume that if you accepted financial impact, you're going to follow it. So just as what was asked before by the gentleman there, that's my blind side.
But they know that financial impact at start.
Yes. So I know the financial impact at the start. So when you come in with your car, that's when we are negotiating with you immediately within the app.
Do you model the threshold for staying based on the value of the vehicle they drive?
No, we don't. No. These are all Nissan employees. They don't drive fancy. Unless there is, I don't think there's an electric Nissan C right now.
Fair enough.
Yeah. So most of them are driving Nissan Leafs. So Nissan Leafs and Nissan Arias. Very. Nissan Ariya actually don't even do bidirectional. It's only Nissan Leaf that can do bidirectional. So we really didn't go that far. And actually, it's a pointed question. How do you know that somebody is actually, because you can change the incentive, for example, to get a more better answer of the likelihood of you accepting it.
Yeah.
Right? We don't do that right now. Right now, our answer is based on pure computational benefit. And for example, you should divide user into 4 groups or 5 groups, for example, right? The kind of car you are driving, the management status you are in, the typical importance of going outside. Because for example, if you have a lot of meetings outside, you're not going to accept it. There's no point giving you. Because I know there's nothing you can do. If your need comes, you have to go.
It's a super clever problem formulation, not just for the transportation, but for property owners. So you hear all over the place, property owners are irritated that they don't have more bodies to build. We could debate why that is, but there are lots of builders in West Palm and Knoxville and elsewhere who would love to find new incentive mechanisms to get more people to stay.
Just quick follow-up, have you gone through the I-Core program at Vandy? Or are you thinking about doing that?
No, so I know I-Core program very, very well. I actually pushed people into that program.
Okay.
I myself chicken out of it. I'll tell you
I'll
why.
tell Shannon that.
No, don't say that. Don't say that. I promise them always that I will one day.
Okay.
Because the reason I chickened out was not because of any other reason. I just didn't have the time. Because I-Core is a very good program, but you really have to do all.
Yeah, I'm a regional instructor for
and everything. It just, you should not do the program if you don't have the time for it. And I just couldn't find the time, and that was the reason I really didn't promise that I would do it. But one of the things is I have a student now who can, so it's not me who will do it. I'll just basically throw somebody else under the bus, right? And they will do that.
And for anybody that doesn't know, the I-Core is a NSF program that helps you do customer discovery to answer the questions that were just being discussed. And if you do the national one, there's actually $50,000 that's given for you to go interview 100 customers, potential customers.
It's a very powerful program. It's a very useful program, and specifically as we are applying for SBIRs and stuff, you have to promise to do that.
Exactly.
And we had an I-Core program here for 5 years.
We're working on bringing it back.
2024.
I'm working to
So
bring
we
it back.
submitted the proposal for that in 2020. We had, for 4 years. Actually.
That must be the
I'll be happy to help you out with that. I was the I for the previous one.
Then I'm gonna talk to you tomorrow. But we're trying to get into 2 different hubs, and one of them is Vandy's.
Yeah, so Vandy does have an I-Core site program.
Yep.
And they come knocking at my door, and I'm like, thank you, bye-bye. It's not because of any other reason, it's just time. You should not promise to do something if you can't do it.
Right.
So I've been chickening out just because of that.
We should let our speaker get to lunch. Thank you again.
I've already, so talked with Greg about this a few months ago.
About what?